last but not least, it's the one-way ANOVAs. So this is a medical problem about diabetes. It does strike anybody at any age, and it affects every part of your body. Did you know that? I did not know that. So let's go ahead and take a look at the data. So here's the data in an Excel spreadsheet, hospital A, B, C, and these are the ages of the patients when they were first detected to have the diabetes. So they're going to see if there's a significant difference between age. So age is your DV, and your different protocol types used at the 3 different hospitals is your DV. That's your group. So let's take a look. You will notice that there's a lot of them, and they're not the same sample size in each one. So, but an ANOVA can handle that, okay? Because again, the ANOVA is pretty robust. So give me a second while I put this into an SPSS spreadsheet. Right, my first IV is going to be group, and it's going to have 3 levels, right? 1 is going to be hospital A, 2 is going to be hospital B, 3 is going to be hospital C, and the other IV is going to be age of patients. That's all these numbers here. So please hold. Okay, so this one's going to be group again. Group. And group is going to be a number, yes. We'll just say which hospital, right? Hospital. And the values were 1, we'll just call hospital A. 2, we'll call hospital B. And 3 will be hospital C. Good to go. And we need to tell Mr. SPSS that it is a nominal variable. No decimals. Okay, your second variable is going to be just age, right? It's going to be numeric, and then we didn't measure decimals with the ages. We could have, but we didn't, so no decimals. And again, we need to tell SPSS that that is a scale variable, a score variable, continuous variable, whatever you want to know. So I already pasted the, oh, I did not. So let me paste the data in. Please hold. Alrighty. So there's all my 1s. Let me get all my 2s. There's my 2s. Whoa, look how many people we got. Now let me go back for the 3s. Okay, here are my 3s. Zowie. That's a lot of people with diabetes, almost 200, so our sample size is huge. And in statistics, we always say the bigger the sample size, the more accurate the data. So, you know, bigger is better in statistics. So I'm going to check for normality of the data. Analyze. Describe me. Explorer. Right? Not the IV, not the grouping IV, but the age. And descriptives, any outliers, plots, the histogram. Don't need the normality. I know what a normal thing looks like. Options, don't need. Click OK. So here we go. Let's see what normality looks like on this bad boy. Wow, yeah, we have a sample size of 196. It's pretty good. No missing data. That's good. The average age looks like about 25. Data's not perfect, but within ranges. Again, extreme values, not necessarily. Outliers, and our data is in fact skewed. Wow. All right, it is skewed to the right. So it means most of the people are between the ages of 0, actually 1, I guess, to 40 here. And we do have several outliers. Okay, I'm just going to go ahead and run it as is because, again, the ANOVA is a very, very robust test. So I'm going to go to Analyze. general linear model univariate because we only have one DV. Okay, and that DV is age, and we put that in that box, and we put the hospital into the fixed factor box. Remember, fixed factor means categorical IV in SPS with the one-way ANOVA. So we're going to go look at the plots. Add. Post hoc tests. Probably, we probably should do the Tukey test. We always do anyway. And options, we want the descriptive statistics because we need those for the APA. We're going to look at the effect size, the power, and the homogeneity of variance. Click continue. I believe we're good to go. Click OK. So here's our analysis of variance. So here's our 3 hospitals. How many patients per hospital? Here's the average age of each hospital, right? Pretty much the same. And this box right here is our Levine's test. It will check to see if we violated the assumption of the homogeneity of variance. How you tell is if this significance number is less than 0.05, then you violated that assumption. All of these assumptions that we're going to be going through this semester work the same way. If the significance value is less than 0.05, then you have violated that rule that's testing. So, but again, we did not, so we're going to keep going. And here is our ANOVA table, just like the one that you guys calculated by hand. Right? You got your sum of squares, degrees of freedom, mean squares, and you now know how to get that mean squares. Is you take the sum of squares divided by the degrees of freedom, and you get the mean squares. Isn't that amazing? And you know how to calculate this F. Right? You're going to take the mean squares of the between group 438.290. You're going to divide it by the error term of 3.56, blah, blah, blah. And you're going to come up with an F score of 1.229, which is very small. The significance value is much greater than 0.05. And so that means there's not a significant difference. Your eta squared in this problem kind of agrees with that. What this means is that roughly 1.3% of the variance between the groups, what's going on, can be explained by the fact that they're in different hospitals. In other words, it doesn't make a difference which hospital these guys are in when it comes to age. Okay? So there is no significant difference between the protocols when it comes to identifying by the age thing. So that is almost it. And let me talk about the power. There's the power for our model is 0.266. Again, that means that what you're trying to do just isn't, the numbers are not supporting what you're trying to prove, that there's a significant difference between the hospitals. This is saying that no, that's not the case. So effect size, last question I'm going to answer. Effect size in both of these has to do with how much of the variance in the DV can be explained by this model. So if you can only explain 1% of the variance, that's weak. You're not explaining anything, okay? And then with your observed power, that is the best analogy I have for that is if your study is like a microscope and you're studying, I don't know, flea wings or something. If you have a crappy microscope, you can barely see what's going on. That means you got a weak power study. But if you have like an electron microscope where you can see, the very molecules that make up everything, that's a real powerful study. So that's what power is, how sensitive your instrument is at measuring what you're supposed to measure. So that's it for that one. Hold on, I'm going to do this last one real fast. So a restaurateur owns 5 different stores and the sales are all over the place. He's going to try to figure out what's causing that by measuring job satisfaction at each of his 5 different stores. Okay, so this is definitely a one-way ANOVA. So let's go ahead and set this up in SPSS because Excel does not do ANOVAs. Not yet. It probably does, but I don't know how. So give me a second. Okay, real fast. The store number, I made the grouping IV. Right, here are the values for that. Right, 1 Lemon Grove, 2 National City, etc., etc., etc. And I told the computer that this one is a nominal variable. Next, I just labeled it job satisfaction. Job satisfaction. And it doesn't have levels, it's just a scored data, so that's what we call a scale data. Okay. So now I want to real quick look at make sure we didn't violate any of the assumptions here. Descriptive, explore, and just the DV. Okay. Descriptives, outliers, histogrammo, don't need the stem and leaf, and we know not to click that one, click OK. So now we're checking on the normality. Right, if your data is skewed, there's tricks you can do to it. We're going to be learning that later. It's called transformation of the data. You can take a logarithm of the data, square root of the data, other tricks. Okay, so we got 50 people in this study, 10 from each store, nobody's missing. Data is a little bit skewed, nothing to write home about. And again, extreme values are not always outliers, and that looks pretty darn normal to me. Okay, so I am quite happy. I'm not even going to pay attention to this box plot, even though it says there are a few outliers. Okay, so there are a few outliers, but the data looks practically perfect to me anyway. So I'm going to proceed with my one-way ANOVA by going to General Linear Model, Univariate, because there's one DV. My dependent variable is job satisfaction scores. My grouping variable is the stored locations. And do I want plots? Sure. And post hoc tests, probably should do the Tukey test. And I think we forgot to look at the Tukey test on the other one, but too bad. And options, I want descriptive statistics, effect size, power, homogeneity. You should do this on every ANOVA. Okay. All right, here we go. There's our ANOVA. How many people in each group? Here's the means. Standard deviations. Here's our Levine's test. What does that check for? You're right. Homogeneity of variance. And we did not violate it because our significance score is way over 0.05, so we can keep going. And here's our ANOVA. Okay. So we got a great big F of 9.572. That's huge. Significance value much smaller than 0.05, so there is a significant difference between the groups. The eta squared is much better. It's about 46% of the variance you can explain with this grouping model you did. So in other words, location does have something to do with job satisfaction, apparently. And your power is very good. It's almost 1. So that means that you have a very sensitive instrument. So you did good. So now let's check our Tukey test, our post hoc test, and see where the significant difference was between which of the stores. Okay, so here's the Lemon Grove versus National City. No, right? This is not less than 0.05, so that means there's no significant difference between those two. Lemon Grove and La Mesa? No. Lemon Grove and El Cajon? No. Boy, they're practically the same. Lemon Grove and the San Diego? Yes. So there's a significant difference between job satisfaction between Lemon Grove and San Diego. Let's flip down here and see any other ones that are less than 0.05. Ah, here's another one. So between National City and La Mesa, okay, so you would be writing this up in your APA formatting because there's your significance under the Tukey test. And there's another one between San Diego and National City. And another one between San Diego and La Mesa. You see, I'm just going down to the significant values here. And then they should start repeating themselves, okay? Like here is El Cajon and San Diego. Up here is El Cajon and San Diego. They're just in different orders. But yeah, there's a lot of significant differences between a lot of these stores. So, and that's about it.